Hello. How are you?
Hello, I'm good.
That's good. How are you doing? Are you like tired? How are you feeling?
Um, I think I'm stressed.
Yeah, tell me about it.
I mean, my test is next week, so that's expected. It's
Uh-huh.
normal. But I'm also really behind on like my Psych Soc Anki cards.
Yeah,
So yeah, there's that. I haven't like been focusing much on Psych Soc, but now I'm like I want to get through all these cards, before the test.
got it. Um, is there anything that you feel like, you know, you're well, like weak in, like particularly speaking, weak in for psych soc?
Um, I can't think. I would say like the material that I have to review would be like the things that are like just the stages of development and all these things
Yeah.
which I just have to memorize them or rememorize them and also probably like auditory processing and like the neuro part of it.
Yep.
um
So that's interesting because you're like a neuro major, right?
yeah, but I want to make sure that I
Hmm.
have it down. I mean, they barely ask any of those questions. So,
I mean,
they,
they'll
yeah.
likely ask you.
Sorry?
Oh yeah, they'll likely ask you stuff like that actually.
Yeah.
Um, I have some, let me see if I could find, I have like some scanned notes from a long time ago when I was studying this. Let me just look for that real quick. So yeah, as I try to look for this, what else? Tell me some more stuff.
Mm, for psych soc.
Hmm.
Um, well, I think the thing I'm most worried about is like seeing a term or a concept that I've just never seen before. And
Yeah.
like maybe it's something that I could have known if I had been exposed to it. So I'm trying to cover all my bases with all those cards.
Hmm. Got it. So, one second. This is my like one of my notebooks. You can kind of see
Mhm.
anatomy, physiology, psychology. So I'll scan the section for you that goes over uh hearing. So like this is the
Oh
ear.
wow, that's beautiful.
Yeah, thank you. Yeah, this is the most inefficient way to study. But because I got like colored pencils and everything like that. Um and then over here it's the full like auditory pathway from like beginning to end. So I'll scan this. But in the shared PDF folder, I have some more scanned notes like of the eye, um, the brain, and things like that. So one of the things that you should know is like the entire like pathway. Like so, for instance, for the auditory pathway, it's sound wave travels through the auditory canal and causes the eardrum to vibrate, and then it goes through the ossicles before while amplifying the sound. And it's basically like uh like if you draw arrows like goes from here to here to here. So yeah, that stuff I would say definitely no, because they likely will ask you. Um because yeah, I've seen them ask you things like that with vision as well, like yeah, with like the crossing over and stuff. So yeah. And also this is my psych like notes also. So, you know, any other stuff you can ask me, I can tell you about from here. But
Um, can't think of them right now.
Sure, sure, sure. It's okay. Let's work on that passage that you sent me. Also, when you review your practice tests for the psych-soc section, um, any word that you see that you don't know, you should make Anki cards for. Have you been doing that?
I haven't been making my own cards. I've just been
Okay.
using like the pawn cow deck.
Yeah, yeah. But so like when you review your psych-soc sections, do you like what do you do when you see like a word you don't know? Like,
I look it up, but I don't like make cards on them.
okay, okay. I would say, um, I mean, is it like when you look it up, does it like stick, or do you feel like you forget it?
I don't know. I feel like I don't know.
Okay, okay. So the thing
Uh,
with psych-soc is that um the good part about psych-soc is that since it's so content dependent, if you know your content, you can get a high score in it, which is why the psych-soc section is the highest like average score. But the it's like a double-edged sword because you if you don't know something, you can't really like figure it out. So what I always tell my students to do and what I do or what I did was every time I took a psych-soc section, I used that as an opportunity to learn new terms because there could be like there's no limit to the types of terms that you can see. And then I would just make an Anki card for each of the terms that I see every time I review, the psych-soc sections. Even if you got like a question wrong, right, if there's a term in the answer choices that you don't know, you're going to have to, I would say to look it up and then make an Anki card for it. So I would say one of the like maybe like tomorrow or something to maybe quickly kind of go through your blueprint psych-soc sections and then maybe like make like an Anki card for each term. So
okay.
because they can ask you like they can ask you like literally like a trillion different things that you wouldn't see like unless you took like 30 practice tests. So yeah, that's what I would recommend for psych-soc. So yeah, continue with the Pancow deck, but do that with the blueprint full lengths that you took.
Okay. Yeah.
All right, so okay, so yeah, let's go over that electrochemistry passage, right?
Yeah.
Okay.
Think- Should I? Do you have it? I think
Yep.
sounds good.
For some reason my do you see a whiteboard?
I see the whiteboard, but I don't see anything on it. It's blank.
It's appearing just blank to me. Let me try ending. Wait, kind of annoying. Let's see. Um, can you try opening a whiteboard? For some reason, when I'm opening it, it's just giving me like a blank screen.
I opened it.
I still see a black screen for some reason. All right, I might have to end.
Leave and come back in. Yeah.
Yeah. So since so here, I'll make you the host and I'll be right back.
Okay.
All right, so All right. So why don't you start reading the passage? And if you see those buzzwords, let me know.
Okay. I don't know why, but I am seeing the same page.
Oh, so yeah, what you want to do is when you click on it, it'll open like a little thing on the bottom, and then it'll be like page like 1 of 4, 2 of 4.
Okay.
Yeah. I tried instead of screenshotting it, I just tried uploading the Word doc that you sent itself, and so it's opening it up with the 4 pages that you can browse, but I just put them separately.
Okay.
Is it working for you?
No.
Okay, I'll
Like
just
I'm not selecting it and I can't like if I were to, I guess I could start reading from the top, but like I can't
here.
change that to
I'll make the screenshot. So one second.
I mean, I guess it's fine if you change it for me when I get there.
Here, I'll just. Okay. Can you see what I added this time?
Yeah. Yeah, I can. Okay, so I can start reading.
Yeah.
So passage 10, a group of students investigated the reactions of several metals with solutions containing metallic ions. Experiment 1, the student placed strips of a metal, X in solid state, into solutions containing different metallic ions, Ym plus aqueous, as shown in figure 1. Okay. Beaker, metal strip, and an aqueous solution with with Y as a cation.
Uh-huh.
Okay. Figure 1, metal strip in solution. So after several hours, they observed whether or not Y solid formed on the surface of the metal strip. See table 1. So they want to know, well, they observed if Y had, I think it's like called like electroplating, electroplated onto this metal or no? I don't know. I think it's electroplating. Results of metal strip experiment. Table 1. Yeah, it's just repeating. So the identity of metal ions, they have the composition of metal strips. Okay, so they have different cations and different like metals bars, like mirror sticks. Um, yeah.
All right.
And
Yeah, go
right.
on.
And so they recorded their observations. A star indicates not studied, so like they just don't have it, and they'll probably ask us things about it. Um,
So let's before we think about that, right? I mean, because when you see the asterisks, you see that like what do you see them for?
what do I see them for?
Yeah. So for figure 1, you can see that.
Oh, for the same thing. Okay.
Okay.
So
Mhm.
like the
Yep.
a solid bar and it's cation
Uh-huh.
same and same. Okay.
Yeah. Because you see up for in the figure 1, you see that the metal strip has a different identity from the cations, right? X and Y.
Yeah,
So
yeah,
so that yeah. So when you see this table now, you can see that for when the solid is the same as the cation, no like result would happen. I mean, it says not studied, so maybe that can be a little misleading, but you can kind of think, okay, why is it not studied? Because you're not going to see anything happening, like because you need the things to look to be different according to figure 1.
okay.
And then from there you can see no change in new solid. So what does that mean?
So no change, like the cation state in solution
Okay.
and new solid. I've been thinking of like electroplating, so like it's like I don't know, plating onto the metal. That's what I'm thinking.
Tell me a little bit more about what happens when something gets plated on.
So I know that it's an oxidation reduction reaction.
Okay.
And so there must be a reaction for it to go from like a solute into a like a metal. I know it has to do with like reduction potentials, but I'm not confident in that area. Yeah.
Got it. So, okay, so let's just think about it like physically, right? So, if we look at figure 1, right, you can see that the Y, the cation is in the aqueous solution, right?
Yeah.
And then what do they observe happening to Y once it plates onto X?
From like the graph now, or
So sorry, Y goes from aqueous to what?
to solid.
Yeah. Okay. Now, if it's going from aqueous where it's a cation and turns into solid, that should be like a redox type of thing, right?
Right.
Which one?
Um, so it's going from being positively charged to, I'm thinking neutral. So it means that it gained electrons.
Yep.
So it was reduced.
Yep. Good. So we're going to need our Ym plus aqueous to, let's add, an electron to that to give us Y solid, okay? Now,
Yeah.
make that look a little better. Okay, now, could you ever just have a reduction like this, or do you need an oxidation too?
You need an oxidation.
Good. So what do you think that oxidation would look like?
I'm thinking X is
X what?
losing electrons. X solid
Good.
is losing an electron and becoming like its cation.
Good. So that would be what gets oxidized, right?
Yes.
All right. So now if we take a look at the table, we see that so like what happens when you have aluminum strip with copper ion? What's that new solid that forms?
So just copper solid
Yep.
is formed.
Mm-hmm. Yep. And there you go. So the no change is no change. The new solid would be like composition of metal strip would be like X. And then these guys would be like Y, M plus aqueous, right?
Yes. Yes.
All right, cool. Um, okay. You can continue.
The students place the solid strip of each metal into an aqueous solution containing ions of the same metal. Complete circuits were established.
Oh. Okay.
Okay.
So yeah. So now,
So
yep.
so now they have like this is the cell, like I guess this is where they um have probably like the electrochemical cell.
All right. Tell me about electrochemical cells.
Mm. So they can be either like electrolytic or they can be like galvanic or voltaic wave.
Oh. So what's the one that they're showing us here?
Um,
Two.
and they can also be concentration cells, I think.
So think of them more so in the broader categories.
Um, what are they showing us? So I know like for the galvanic or voltaic, it's like spontaneous, so you don't have like an energy source. Versus for the electrolytic, you do need like a voltage source in order to see something. So I guess if I know if I have a voltage source, then I or not, then I would know.
So 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 you said that um so you said that okay, so when you said spontaneous, that would mean something about delta G, right?
Yes.
What would that mean?
It would mean negative delta G and positive EMF.
Yep. And we could say like just like E like the cell something
Cell
like
potential. Yeah.
and what did you say about the cell potential?
It has to be positive.
Okay. Now, so this would be electrochemical cells, also known as galvanic cells. Sorry. Oops. Also known as concentration cells, also known as, I guess, voltaic. So all of these are meaning the same thing, essentially that well, yes, it's spontaneous and its cell potential is well, delta G is negative, cell potential is positive. Is there any like formula that can bring these?
Um, I think there's two, right? I guess if you consider enthalpy, or do you want like without enthalpy?
Well, with I think what you're thinking about, the one with enthalpy, that wouldn't have the cell potential though, would it?
Right, right, no. Um, so it would be like the delta G is equal to negative NF and the cell potential.
Very good. Okay. Good. So now okay, so you know this stuff, so that's good. So what I would emphasize now would be that this is in this type of electrochemical cell, you're having um should I put this? You're having a chemical, so there's like a chemical like chemical gradient, so you're converting chemical energy into electrical energy. And by chemical gradient, I mean like separation of molecules. So like we have X solid and X cation on one side, Y solid, Y cation on the other side. We would need, like, since they are not the same, like X is different from Y, they should have different reduction potentials. And do you remember how that worked? Reduction potential meaning does like I guess does something having a high reduction potential make it more likely to be reduced or oxidized?
I think reduced.
Huh? So maybe I'll say like whoops. Reduction potential is proportional to I guess like likelihood of being reduced. So maybe I'll just write reduced like this. So, okay. Now, so yeah, since you have a chemical gradient with X on one side, Y on the other side, there's a potential there between the two. So electrons will have to flow from one end to to another end. And as it does that, it can cause this light bulb to light up. So you're getting electrons being transferred through the redox reaction. And I think I usually draw like a battery because I think it's easier to conceptualize. So like in a battery, I just draw like the positive end, the negative end. So right there, that shows you that there's a battery that the way that I drew it. Oh, and by the way, all of this stuff is how a battery works. So like all these words, there's so many, right? But that's how a battery works because if you think about it, you're using a battery to power electric things, right? So you're using a battery to create electrical energy. Now, the concentration cell or the battery that I drew down here, there's a positive end and a negative end. And this is going to be an example of like a lithium battery, which has the same, it doesn't have like X and Y. It has high concentration of X, low concentration of X, but you still have that charge separation, right? And I mean, it's more than charge separation. You have different, all right, so charge separation could also be the change in reduction potentials. So if there wasn't, so if I drew the example with the X, Y, like the strips and stuff, if the reduction potential of X is equal to the reduction potential of Y, what would happen?
Guess nothing.
Nothing, right? Because you don't have that gradient. But the same thing with this. You have a positive end with more lithium ions, the negative end with less. And there's a gradient there. That means that there's a potential there. And that's what voltage is. It's potential. It's something that doesn't really do anything on its own, but when you connect the ends, it will cause the redox and the electron flow to substantially happen. So like this battery, I can connect it to a light bulb as well. And it's going to light up the light bulb because electrons are going to be moving, right? But if it'll continue until you have equilibrium, at which point you'll have a dead battery, right?
Yep.
So yeah, now the opposite is an electrolytic cell. And it's typically always called that, but you should also know that the three things you can do with electrolytic cells are electrolysis, which is, as the name suggests, using electricity to cause like breaking of a bond. So that's like in submarines where they take H2O and they use electrolysis to turn it into, oxygen and like H2 gas. So that's electrolysis. There's also electroplating, which is, if you want to plate something, that's kind of like the example we have in the top of this passage. And lastly, just recharging a battery. So this means that the electrolytic cell will have a delta G, right? That's positive, and a cell potential that's negative, right?
Yep.
And since you're using since you're like trying to recreate that chemical energy gradient, you're using electrical energy and converting that back to chemical energy, right? So, any questions here?
So when you have a battery for the electrolytic cell, it's doing what you just said it was doing, but I guess like if it were, it's generating a potential, but yeah, I guess that's what it's doing, but I'm struggling to like understand exactly what it's doing, and I guess it all depends on what type of electrolytic cell it is. Is it like sending things against the gradient or
So all electrolytic cells would be doing the same thing, essentially. I mean, in the sense that you're taking you're running the battery thing backwards, essentially. So if I drew that battery example again, whatever, here's a light bulb, but this is like plugged in to like an outlet. What happens is you'll have a momentary, so you'll have electricity coming in, and when it comes in, it's going to want to go. So okay, the in between here is when this is 0 and that's 0, right? So it's going to want to recreate this with the plus end up top and the negative end on the bottom. So when it does that, it will momentarily put a negative charge up here and a positive charge here, just so the electrons can go and accumulate on that positive end. And electrons will not be moving like from the negative end here. So you're just having the electrons flow into that anode region. It's still called an anode. And the top is still called a cathode. And something that can be confusing is that it seems like the anode is gaining electrons.
yeah.
But we know from anox that the anode is supposed to be where oxidation happens. So why is this still called an anode? So the reason that it's not that it's still called an anode is because anox and red cat, right? That is when you have the redox pair, meaning when you have electrons, a redox pair means like you have electrons from the thing that gets oxidized go to the thing that gets reduced. They have to both be there. And in an electrolytic cell, we are not having electrons going to or from the anode to the cathode or cathode to the anode. We're not having that. We're just having external electrical energy or like electricity accumulate on the anode end.
Okay.
Yeah, but yeah, redox will require a redox pair. So okay, any questions? Other questions? Okay. So all right, so yeah, back to this, and yeah, you can continue reading.
Okay, so they have figured. I'll just read this again. The students place a solid strip of each metal into an aqueous solution containing ions of the same metal. Okay, complete circuits were established. So they have no voltage source, so I know it's like this galvanic. They have two different metal identities, so like two different plates, and they have two different cations, and each cation corresponds to the metal plate identity. And they have a salt bridge, which, if I remember correctly, it's like to balance out charges. I'm not sure.
Yeah,
Yeah.
because they mentioned a complete circuit. So, so you may have electrons going from one plate to the other, but the salt bridge enables the cations, to go in that opposite direction to make that complete circuit.
Okay.
Mhm. If you got rid of the salt bridge, the light bulb would not light up.
Why?
Oh, just because you don't have a complete circuit, right? Because what you have,
Oh, I see. It's like connecting it. It's like this.
yeah. Because you're gonna have like, let's say X, whatever. Let's just say that electrons are going from X to Y,
Mhm.
right? But if without a salt bridge, they would not be able to go back to X. So like if electrons are going that way, you'll have some ion go in that opposite direction.
I see.
Like it
Yeah.
would be for the same reason that something like this like wouldn't work, because you don't
Yeah,
have that other end attached back to the like this part.
I see.
Yep. Yeah, so like circuits will always need to be loops.
Okay.
Yep.
So finally, the students checked a general chemistry text to determine a standard reduction potentials for the following reactions. They have, I think that's lead. Is that lead? 2 plus 2 electrons, solid, and the reduction, which is negative. And for copper, they have copper plus 2 electrons, copper cation plus 2 electrons, it's copper solid, and they have the reduction potential. So for this second one, it's positive reduction potential. And for which means it's more likely to be reduced than, I guess, if I were to compare it to the lead one.
Okay. What would the reduction potential be if I put a 4 here? So like 4 copper plus 8 electrons yields 4 copper.
Mm, I am tempted to multiply it, but I'm not sure if we're supposed to do that. Or if it's like an intrinsic property of the metal, which it's probably an intrinsic property of the metal, is what I'm gonna say.
Yeah, I think it's a intensive property. Like as opposed to extrinsic property.
Okay.
So like, so what, okay, so like for instance, okay, so like, yeah,
Because I guess like you'll always need like 2 electrons to like reduce one like copper cation, and this won't change regardless of the amount that you have. So like this number here is like for just one ion, like how like likely is it to be reduced?
yeah,
Sort of like when we talk enzymes, you're like, yeah, I don't know, but yeah.
yeah. So like some other intensive properties would be like pressure, things where like an increase in the quantity does not cause an increase in the intensive property. That's how you can tell if something's an intensive property. So, and then extensive would be like where the amount matters. So the example that I think of for extensive is, if you did like the delta H of a reaction and then you had to put in like, the heats of formation of like this reactant plus this one. If you have double, one of these things like a coefficient, you would have to multiply that by 2 because when you have the bond energies, that stuff is extensive property because, well, it's enough to break one bond. If you needed to break 2 bonds, you would need twice the amount. So good job. Okay, so all right, so yeah, so now what do we do? What do we do with these reactions, like to make a redox reaction?
We need to oxidize something.
Okay.
Um, well, in this thing, they're solid, so I guess you have a forward and you have like the inverse reaction, reverse reaction.
So just think about what we mentioned before about um like maybe the proportionality of something that we talked about. Maybe up where I wrote here.
I see. Chemical energy, electrical energy. So
So
I don't know how it happens, but I know that they may cross onto the other side, but I don't know how that happens.
so
Maybe
so
it's like the other. Yeah.
what I was trying to point out here is, so what did I write in red here?
Chemical energy equals electrical energy.
Oh, so that means gets converted to. But what about
Yes.
that?
E reduction is proportional to being reduced.
Yeah.
So they are reduced, but
So tell me, so like the proportionality would mean if you increase the reduction potential, what would happen?
you will get reduced if you increase the reduction potential.
Uh-huh. So that would mean whichever has the higher reduction potential will be the thing that gets reduced, right?
Yes.
Okay. So which one would that be?
The copper.
Good. So the copper will be reduced. Then what else happens?
Um, I guess, well, I don't know. For this figure too, am I assuming like copper is on one
You
side and
don't have to worry about the figure now.
like
It,
are these together? Like I guess since this one is if they were together, I would think that yeah, copper would
here,
be reduced
let's say
and
we
lead would be
let's say we have one reaction with a reduction potential of 2. Let's say another with a reduction potential of 4, right? Which one would be reduced.
So Y would be reduced and X would be oxidized.
Good. Good, good. So, okay, so like Y would then look like Y, let's say cation plus an electron yields Y solid, right?
Yes.
But the X one would look like what?
X solid goes to X cation plus an electron.
Good. So we're taking the reduction half reaction and we're writing it backwards, right?
Yes.
Now, what would its oxidation potential be?
The inverse of the like the flipped sign of the reduction.
So did you say inverse or flip sign? Which one?
Flip sign.
All right, so -2.
Yeah.
And then what would the overall cell potential be?
So it's so it's 2 minus 2, so 0. Wait, sorry, 4 minus 2, so 2.
Good. And you see how I wrote 4 plus -2?
Yes.
Good. That's like, because I know it's the same thing as 4 minus 2, but it's not completely accurate to say that. It's more accurate to, like, I say that there's no, so one of the things I say about math on the MCAT is there's no subtraction, there's addition, and there's addition of a negative number. And there's no division, there's multiplication and multiplication by a reciprocal. So, because this can come in handy, like if you had, let's say, this is a vector called P, and this is a vector called Q, and we need to figure out what is the sum of P plus -Q, right? So -Q would just be like Q except in the opposite direction, so that's -Q, but you're still adding these two vectors. Like it might turn out to be subtracting at the end, but you're really just adding a vector that's in the opposite direction. So, okay, cool. So here we can see that the lead turns into, or should be oxidized, right? So this should be going that way, right?
Yeah.
And then the oxidation potential should be what?
0.127.
Yep. Good. And
Yeah. So in that case, it would be like just adding those to get the cell potential, right? Like, okay. And it would be okay. I just sometimes the equation that I've seen in like textbooks is like has a negative sign already included.
yeah,
And in that, yeah.
yeah. You're thinking of the one where it's like anode minus cathode type of thing. Is that what you're talking about? Like what like a cell potential that's cathode. Whoops.
Probably, yeah. I can't remember exactly, but probably.
Yeah, that's what I see how I see that it's written like that in like the Miles Down deck and stuff like that. So this would be good to remember also. Like I prefer to do like oxidation potential plus reduction potential. But sometimes it's easier to do it the way that's above that, where it's the cathode potential minus the anode potential. So I would remember both.
Like, in what circumstances would it, I guess, I'm with you that I like the plus one. It's more like I don't remember which one is on the left and which is on the right. Like
Yeah.
I just think of the yeah, the one you told me.
Uh-huh.
I guess perhaps if we're not like if we're just like shown the cathode and shown the anode, it might be easier.
Yep. Yeah. So I would just, yeah, I think I saw like maybe one example before in which it was easier to use that relationship, but I don't remember the exact circumstances, so I would say to know how to do both.
Okay.
And the reason that it's that minus sign is because nothing's getting kind of nothing. So like the way that I did it here means that you need to figure out which one is oxidized and which one is reduced. Whereas this one here you can use without needing to figure that out. But
Okay.
yeah. So okay. Any other questions here?
Nope.
All right. So let's see. So I think the first question. Which one is the first question? Is it
This one.
okay? Yeah.
Um,
Increase the current by doing which of the following?
um, the answer's right there, so I'm just gonna try to explain why the others are wrong.
Oh yeah.
Using electrical wire with a smaller diameter, you would decrease the current by doing this, I believe. And my thought process here is like you would have maybe like less electrons flowing per second, but also like they're bumping more into the sides of the wire.
Oh, sorry, I just put the black boxes. So can you tell me again what you're saying about A?
Like if it's a smaller diameter, you would be decreasing the resistance. Sorry, increasing the resistance. So decreasing the current. One, because the formula for resistance is like resistance equals like resistivity times length of the wire over area, which so like if you increase if you decrease the diameter, your I don't know, I have to do the math, but the case is that the resistance will be increasing.
Yeah, so let's think about okay, so okay, yeah, so you said this, right?
Yeah.
So in other words, this is inversely proportional to area.
Yes.
Now, how can we bring current into this?
Voltage equals current times resistance.
Uh-huh.
Or like voltage
What's the
over resistance equals current.
So what's the proportionality relationship between um current and resistance?
They're inverses, so like inversely proportional.
Good. So now if the um resistance is inversely proportional to the area and current is inversely proportional to resistance, current should also be proportional to area, right?
Yes. Right.
So they're asking us what can increase the current. We want to look for something that may say uh to increase the area, right? The cross-sectional area. And A is the opposite of that, right?
Yeah.
So that would do the opposite. So okay. What about B?
Um, Increasing the temperature of the electrical wire. I don't know. Temperature always plays a role and I never know how.
Oh, plays a role, you're saying?
Oh,
Oh yeah, yeah. So you're saying it plays a role?
yeah. Yeah, I think we had this conversation. I'm like, how does it affect it? But it always has an influence.
What is the definition of temperature?
Um, I'm thinking heat, but that's probably not right. Um,
They're distinct. They're related, but yeah. But what yep.
increase in kinetic energy. I don't know. I guess I don't know like what the definition would be, which is
All
a
right.
simple thing.
So here we go. Heat is energy. Okay. Temperature is the average kinetic energy of molecules. Okay.
Yep.
So heat is the actual energy part of it. Temperature is and if you add energy to something, the molecules will start moving around faster, which would give you a higher temperature. And you can think of this also as when you have, do you remember like the heating curves that were like
Yeah.
something like that? So on what's on the y-axis here?
Heat.
Um, try something else.
Um, temperature.
All right. And the x-axis?
Um, I don't know.
So what can we be adding? Because from left to right on the x-axis, we're increasing whatever x is.
Okay.
So what would you add?
So
Yep.
like heat then?
Huh? Okay. So from left to right, we're adding heat. Okay. And we see that sometimes the heat added causes the temperature to rise, but then sometimes it doesn't. What's up with that?
Like state change.
Uh-huh. So what's happening when heat is being added and the temperature is increasing is that the average kinetic energy of those molecules are going up.
Yes.
And then when they reach that plateau, the kinetic energy of the molecules are no longer, I mean, they're still traveling fast, but the heat that's being added at that point is contributing to breaking the intermolecular bonds between the molecules. So essentially, so if you had like a solid here, once you come here, you're converting the solid to a liquid. And so the energy is going to make that phase change happen instead of increasing the temperature once you get to that
Okay.
point. So remember, heat is and so like heat is that type of energy. So you can also just think of it like that. And so that heat can be transferred, but temperature isn't a specific thing. Like if you had something like this, so like let's say this is a high temperature area, a low temperature area, heat, which can be written as Q sometimes, heat is being transferred from the region of high temperature to the region of low temperature. Right? So
Yep.
that's, you know, the difference between heat and temperature. So yeah, definitely have that in mind. So now, okay, so now that we know that what temperature is, what do you think increasing the temperature of the wire would do?
Um, when like an electric wire gets heated up, it's never a good thing. So that's I'm not thinking I don't think it's increasing the current. If anything, it's like,
So why don't you tell me?
oh, I think it's making like the particles going through it like move, have higher kinetic energy. Um, yeah, that's what it's doing.
Yeah, so think about what happens when you get resistance, right? So, and it was good that you were thinking of it on a molecular level. That's going to be like not even a molecular level, like an atomic level. Because you know that resistance is like the electrons brushing up against the atoms of the wire, and that causes friction. And friction, something to know about friction is that uh, it causes energy to be lost to the environment in the form of heat, right? So
Yeah.
if the resistance goes up, the temperature of that wire or the resistor will go up as well, right? So we know that resistance is proportional to, maybe I'll say like temperature, but maybe I'll also say like heat. Um now so okay, so that means that so since things with a high resistance uh release more heat and have its temperature increased, we can, I guess, then go from there and then see that back to the relationship, the inverse relationship of current and resistance. uh we should get, like, if you increase the temperature of the wire, you should get a smaller current, right?
Yeah.
So, like there's things like superconductors and stuff. Like, it's obviously not on the test, but uh when superconductors can be conductors, like, metals that conduct electricity, but if you like super cool it to like really low temperatures, I think like close to like absolute zero, you don't have any, like, yeah. Um, and so that's for superconductor, but there's also semiconductors. So like, um, if you like were to look at like your computer's like motherboard or whatever, like the green kind of chip that's made out of like silicon, because it's like a metalloid, and it can have some of the properties that you want in a conductor, like ability to conduct electricity, but it'll also have some properties that you don't want in a typical metal conductor, in that it won't conduct heat as well. So it doesn't heat up all the time. So yeah, so the temperature is going to do the opposite.
Decreasing the concentration of the cations. Um, it's figure two. So if we go back, like the cation um are necessary and like they are what's like are being reduced and like driving like the circuit, sort of like the electrons in this case is what I'm thinking. And so like you would decrease the current if you decrease their concentrations.
Okay.
Also, like the premise of a concentration cell, I guess, is like things are moving because of a concentration difference. Like if you decrease like what you have of each, like you're going to decrease the current.
Uh-huh. So I just threw in this image here um to show you like the effects of temperature.
I see. 20 degrees, the metal atom and a free electron. Free electrons colliding with metal atoms as they flow to the right. Okay. And it's at 70 degrees, so very hot. As the temperature increases, the atoms vibrate, and it is harder for the electrons to flow, increase in resistance. Okay, I see. Because like I guess what is depicted here is like when they vibrate, they're like pushing the electrons in the opposite direction, and so they're resisting their motion.
Yeah, it's almost like so kind of like one an analogy that you might be able to make sometimes is relating Ohm's law to the continuity equation in our blood. Like
Mhm.
that. And so like so what you're having happening in the 70C example is that it's kind of like the equivalence of um turbulence, whereas when it's at 20C it's just like laminar flow like that. But okay, cool. So all right, so you said about the concentrations.
Yeah, that it would decrease the current, sort of like premise of how a concentration cell works.
Uh-huh.
Um, that it's like you have less of the reactants, like you'll just have less movement of electrons, and so you'll have a lower current.
Uh-huh. So they're yeah, it seems like they're decreasing both of these concentrations. Um, so okay. So yeah, we can I mean that wouldn't change the cell potentials or anything like that, right? But it will affect the number of electrons, right? Because if you don't have those cations, that salt bridge is gonna like run out of things that can pass through it. So okay, good. And
Yeah.
then D, replacing it with one that has a resistance of 0.2.
So our current one has a resistance of 0.5. So if you decrease the resistance, you would be increasing the current by like Ohm's law. So it has to be D.
Okay, what if that light bulb was in parallel?
Um, if it were in parallel and you or giving it a lower.
Oh, you know what? Sorry, the example like it actually doesn't work with the parallel because that's you only have one light bulb. So never mind. But good job. So yeah, so okay, it'll be, if you essentially decrease the resistance, you'll have a higher current, right?
Yeah, I still want to review that. Like, when it's in parallel and you're like adding resistors, I know that when you remove a resistor, instead of instead of decreasing the resistance, you're increasing the resistance. That's correct, right?
When you say
Like
remove,
when you like eliminate a resistor that's in parallel, you end up increasing the total resistance, right? Um, Now if you add one in, you would be decreasing the total resistance again, because like the more you add, the lower the resistance is, just by the like equation. But yeah, I guess.
yeah. So let me ask you this. Let's say you have these choices, um, and let's say So let's say you're given a focal length of 4, an object distance of 2, and you need to find the image distance. Without doing any calculations, which should be our answer?
Focal length is 4. Object length is 2. And we don't know the image length.
Yep.
Gosh, no calculation. Um, um, um,
Let's start with this one. And these are in parallel. And you still have the choices of 3, 5, 6, and 1.
okay, so if they're in parallel, they have to have a lower resistance than like either one. Either of like of the it has to be lower, so I would say probably 3.
Well, you said lower, right?
Yeah.
So what would
I mean, it could be 3
so okay.
or 1, but
When you said lower,
yeah.
you when you said lower, like
Like the total resistance is what I'm thinking
huh?
has to be lower than like 4, and like if it's not additive, like it's not 4 plus 2, so it has to be lower than 6 is what I'm thinking. Like it has to be lower.
So let's think about it, right? So you said lower, um, but isn't 3 higher than 2?
Yeah. I don't know. I was thinking it could be 3 or 1, and I just went for 3 because it's an intermediate, but
Uh-huh.
I'm assuming it's 1, but
Yep.
um uh
Yeah.
okay.
Because
So
like
it will be lower than either one of them.
this is the equation, right?
Yes.
And so a reciprocal sum will give you a value that's going to be smaller than either of those other resistances,
Okay.
right? Because it has to be every time you're adding a resistor, you're allowing electrons to you're offering electrons to go through like a less congested path, right?
Yeah.
Which is why you have a reciprocal sum. Because if we got rid of resistor 2, we would have to go through resistor 1, which is 4, right? But let's say we get rid of resistor 1, we'd have to go through resistor 2, which would be 2, right? So if we have both of them, then it'll be less than either alone,
Okay.
right? So, uh, okay. So now apply it to this. Or maybe
Um,
I'll make an adjustment here. So let's say whoops. Let's say that whoops. Let's say that we need to find focal length.
so it would sort of be the same principle that it has to be lower than 2 and 4 because it's also a reciprocal sum. So like 1.
Yep. So, it's probably not 1 because like I didn't like make the math be but I want you to be able to see when you have a reciprocal sum that your reciprocal sum must be smaller, not just smaller than one of the terms, but smaller than either of the terms,
Okay. Let's
right?
see.
Okay. So, all right. So back here, oh yeah, so I guess I asked that because we're replacing it with one that has a lower resistor. But okay.
Mhm.
Are you ready for the next one?
Yeah,
All right. Try that.
the next question, right?
Yeah.
When a strip of zinc is placed in a beaker containing 1 moles per liter of hydrochloric acid, H2 gas evolves. Okay. If a strip of aluminum is placed in a beaker containing 0.1 moles per liter of hydrochloric acid, does H2 gas evolve? Let me think. You have a strip of zinc and you have a reaction happening. And they want me to know if I use aluminum, will I have, like, is aluminum, does it have a high enough reduction potential to be reduced and like have a reaction with hydrochloric acid is my guess. So ideally I would hope that I had like the reduction potential of like aluminum and also of the other reactant. Which I guess it can't be hydrochloric acid, can it?
What?
I guess and hydrochloric acid.
What about hydrochloric acid?
Like, do I need a reduction potential of that as well?
Well, let's see what they give us.
So I have aluminum in different metal strips, and I have no, I don't have anything like numbers here to work with.
Correct.
So my reaction is like wait, is it on? Let me just go back and check. Zinc, hydrochloric acid, aluminum, hydrochloric acid. So I have zinc and hydrochloric acid and aluminum and hydrochloric acid. It seems like aluminum requires like 3 electrons and zinc 2. I don't know if that says anything.
Oh,
Um,
what about it though?
sorry.
What about it?
I'm thinking like it needs 3 electrons, so like in order for it to like become solid or like precipitate or like form a solid, like it needs more electrons. So I'm thinking it's probably harder, perhaps, I don't know, to reduce.
Um, well, you would just need to balance like the coefficients and stuff, right?
Um,
Like for instance, Al3 plus 3 electrons gives us
mhm,
Al solid. And then the other one you said was zinc.
mhm.
Zinc 2 plus 2 electrons gives us zinc solid. So we would just multiply this by 2, this by 3. Whoops. So then we would get 2 of aluminum 3 plus 6 electrons yields 2 aluminum solid. And this turns into 3 zinc 2 plus 6 electrons gives us 3 zinc solid. So that's fine, right?
Yeah.
Like, because is this changing any reduction potentials? No.
No.
So don't worry about the like if one's +3, if one's +2, because you could just fix that with the balanced equation. But we know that the coefficients in the balanced equation isn't going to change reduction potentials. So let's think about, this is I think a very good question. Because so like pre-meds are used to like, okay, I need that, I can solve this, it gave me the reduction potentials and I can do it from there, but we're not really given those, so we're gonna have to be a little bit more creative here. So what can we do?
We have to look at this chart, I guess.
All right.
That's the only place in the whole passage that have like aluminum and zinc.
Okay.
And see how.
So what we're trying, so what we what would really
Oh, I think because
Oh.
like, I guess you could compare, right? Because like aluminum and it's reacting with all these other things. None of them have anything to do with hydrochloric acid, but like, I guess I know like, how reactive it is. So like relative zinc, how reactive it is relative to aluminum, just by seeing like the relative reactivities on different metals.
All
That's what
right,
I'm thinking.
so continue with that.
So on with like the first one, it did no, I don't know, not studied. So aluminum seems to have a very low reduction potential
We
just
can't
by.
we can't tell though based on that, right?
No, but I guess compared to zinc.
All
Wait,
right.
you can't tell. Shit, you can't tell. Because it's exactly, I was looking at this.
So okay.
Yeah.
We can't tell when it's the same thing, okay? But
Yeah.
you can tell when it's not the same thing. So let's just pick one. It doesn't have to be the one in the question stem. Like, why don't we pick this?
Yeah. So copper has a higher reduction potential than aluminum
Tell me how, or like what?
because it was able to reduce by aluminum solid.
Okay. So because the copper 2+ turns into copper solid, right?
Yes.
So that means copper gets reduced, right?
Yes.
And that means aluminum gets.
Oxidized.
So now what can you now bring it together
Um,
in in terms of, so which would have the higher reduction potential?
Copper.
Yep. Good job. So yeah, this is a good question because it forces us to think like, conceptually based on qualitative information rather than quantitative, right? If aluminum solid with copper are mixed, the new solid forms, which is copper solid, which means that copper is what is going to be reduced, which means the reduction potential of copper is higher than the reduction potential of aluminum, right?
Yes.
Okay, good. So, all right, so now they mentioned in the question, um, zinc and aluminum, right?
Yes.
So let's do that. So here, right? All right, what does that mean?
It means that zinc has a higher reduction potential than aluminum.
Good.
Hey, they mentioned zinc. Is it zinc?
Oh yeah. Yeah.
Yeah, it is zinc.
Yep. So let's
Okay.
here.
Yeah.
So what do we do now for this question?
Okay, let me go back to the question.
Yeah.
So zinc has a higher reduction potential than aluminum. Zinc is reduced if you have aluminum in the beaker instead of zinc, which has, well, I'm assuming that like hydrogen gas evolving, does that make sense? Is
Yeah.
equal to like hydrogen being oxidized and zinc being reduced, and I might have that flipped. But that's what I'm assuming right now.
Good. So,
Um,
so okay, continue.
um, um,
So think about what you're saying about the hydrogen.
hydrogen is reduced. It is, is it reduced? Wait, it's going from plus to solid, not charged. Yeah, it's reduced. So hydrogen is definitely reduced. In
So
with zinc.
with zinc, right? So
Yes.
what would its reduction potential be relative to zinc?
Higher.
Good.
I see why this is a good question.
Yep.
So
So what do we do
we
with
have an order now. We know like the reduction potential for us for hydrogen is highest. Then we have for zinc, and then we have, so yeah, then we have
I wrote zinc
is
twice.
that zinc? Yeah.
No, my mistake. Oh, so
Yes. Then we have for zinc, and then we have aluminum. So we have like a hierarchy established. Now if you use aluminum, will hydrogen be reduced? And I think it would, because hydrogen has the highest reduction potential in this hierarchy that we made. So yeah, it's like if B is greater than C and A is greater than B, then C is less than A, something like that. Yeah.
yeah, I forgot. It was like that was like they taught us like in elementary school, like those properties,
Yeah.
right? So like, okay, excellent. So if hydrogen can cause zinc to become oxidized, um, and we know that the reduction potential of zinc is higher than that of aluminum, that must mean that aluminum must be oxidized, right?
Yeah.
So what will our answer be?
B. Aluminum is oxidized and hydrogen is reduced.
Excellent.
Right.
Good. Yeah, it's a good question because we don't have these reduction potentials. We have to use that table to it's like, figure out like logically what's happening and then, establish. Oh, I completely realized that I also wrote that wrong. So there you go. Okay, cool. Cool, cool, cool. So, all right, what about this one over here?
Assume that a circuit similar to that in figure 2 is set up in which X equals aluminum and X cation equals aluminum 3 plus, and Y equals copper, and the cation equals copper 2 plus. Which of the following reactions will occur? I see.
Mhm.
So we're with aluminum and copper. And I think that like we'll know like which one would be a solid. Like the solid would be the one that is uh reduced. You sure? Okay, I have to check that. Wait, unless we were giving the, no, we were giving the equation for copper, but not for, yeah, so the solid would be reduced. So we just have to look and see between like aluminum and copper, which has the highest reduction potential first, is what I would say. And let me see the graph again, the chart again, probably. Aluminum and copper. So aluminum and copper, you have no change. Copper and aluminum, you have a new solid.
So wait.
Wait,
First?
sorry?
Oh, okay. So okay.
Yeah, so it says that like when you have the solid aluminum and you have the copper aqueous, it does electroplate. So like copper has a higher reduction potential. So copper should be the one that's becoming a solid in the equation. So like let me see back. So we can eliminate A and we can eliminate B. So now it's between C and D. And the coefficients are different.
Yeah.
Yeah.
What I did over here with the aluminum and zinc here.
Yes.
Yep.
Yes, I see it.
So the coefficients are there just to balance it, right?
Yes.
Okay.
So we have to have a balance here, right? Okay, between C and D. Right. So I guess we have to balance the electrons as well as you did before. Right?
Mhm.
So like like is aluminum the
So
I'll think of the copper first. I think it's easier for me.
yeah.
So you would need 2 electrons per copper. And like I guess like there's 3.
Try writing it out.
Like the half reactions. Or um,
Did you write something similar to what I wrote here?
I wrote the bottom one. I
Huh?
have not written the top one. Yeah.
So yeah, so why not?
Just don't know if I was doing this right. So I wrote the one you have in the bottom backwards. Like not backwards, sorry. I have,
It's
like,
okay.
I'm trying to do like two, see, like the two that they have. And then I'm trying to balance it out with the number of electrons, but that's not helping. Like the
So-
two, so cute, like, yeah, 2 units of copper.
let me ask you this. What if we had something like this? Something like, or rather, something like that. Or maybe this. So the H2O turning into O2 plus H2. How can we balance that?
Um, oh, I see. So you would have to do, you can't just, you have to multiply both sides of the equation. So I guess there's the 1/2 O2 plus H2. H2O. Can't do that. Can't do that. So I could do 30.
You could do the half
I could do a half.
like that.
Yeah.
So here, like, it's just one equation.
I can just make it a whole number if I wanted to by multiplying both sides, like 2H2O and then O2 plus 2H2.
Uh-huh.
Okay.
So if we go back to this, the aluminum thing here, right? Aluminum has the 3 plus, has so in when we take two half reactions and we bring them together into one, what should cancel out should be the number of electrons. So for instance, so if we had like if we combine the two, like let's say aluminum 3 plus 3 electrons yields aluminum solid. And then let's say we did copper solid, turns into copper 2 plus 2 electrons, right? The overall reaction is supposed to be aluminum 3 plus copper solid yields aluminum solid and copper 2 plus. So you can see how, I mean, like, I didn't really check which one gets oxidized, which one gets reduced here, but you can see that whenever you have a redox half reaction like this, that's a reduction half reaction. That's only doing reduction. But we know from redox that one of them has to do oxidation. So let's say that copper is the one that gets oxidized. So I wrote here that I wrote the reduction half reaction for aluminum. I wrote the oxidation half reaction for the copper. And you want your result to be like this. And the result is the combination of these two equations, but we would have to see the electrons cancel out. Right?
Yeah.
So how can we do that? Well, what's a common like factor, I guess, between 3 and 2, or like of
6.
3 and 2. Yep. So we can then do Al3 plus 3 electrons to get 6, we would multiply this by 2, right? So I'll do this again. So if we multiply the entire thing by 2, we get 2Al3 plus 6 electrons yields 2Al solid, right?
Yes.
And then for copper, right? I'm just going to use the reduction half reaction for copper. So this plus 2 electrons yields copper solid. What do we do here? Because we want to get 6 electrons.
Let's multiply it times 3.
Yep. So then you get 3 copper cation plus 6 electrons yields 3 copper solid. Right? And then we can put it together. So I think we determined that, let me go back. Copper, and for copper and aluminum, the copper, it forms the new solid, so the copper one gets reduced. So this is going to be like going sorry. So this is going to stay, and this we have to
Flip it.
yeah. And so when we do that and we bring them together, we would get 3 copper 2 plus 6 electrons yields 3. Well, I guess I could just put it up. Well, no, I'll just write it like this first. Copper solid, and then we have 2 aluminum 2 plus the 6 electrons yields 2 aluminum solid. And since we know that the aluminum gets oxidized, I'll just put it all into one. So I'll do 3 copper 2 plus, well, okay, I'll just draw this for it to be oxidation. So this, that, and that. So then these cancel. And so we have 2 aluminum solid yields 3 copper solid plus 2 aluminum 2 plus. So we see that. Let's make sure that, everything's balanced. So 3 copper on the left, 3 copper on the right, 2 aluminum on the left, 2 aluminum on the right. We have 2 plus. Oh, yeah, 2 plus charge on the left, 2 plus charge on the right. Or I should actually say 3 times the 2 plus 2 charge would give us a 6 charge on the right, on the left. And then the 2 times the... Wait, I think I messed this up because I put in different values. I put in the same values for this and this. My bad. The aluminum is the 3 plus. So yeah, 3 plus there. Times 2. Yeah, it'll just be that.
I see.
Uh-huh.
When you were checking for balance, second time around, you said you just had to multiply. So what are you multiplying? Are you multiplying the charges?
Oh yeah, so just like this example, where in typical stoichiometry we have the subscript that we have to balance.
Yeah.
On the left, for the charges, it's essentially the same thing except it's just a superscript.
Okay.
You would need that to be balanced.
Okay. So, here, I just want to make sure, because I feel like that would be a good shortcut, perhaps for this equation. I haven't seen it for this question. Maybe, I don't know. I don't know if it would be equal, but like, so you're multiplying like the 3 times the 2 plus? Is that correct?
Uh,
Here?
yeah.
And then you're like adding it to 2, like
Uh,
6 plus 2, or no?
Um, when you say adding it to two, oh, like this and this.
Like to the last equation.
Huh?
Uh, yeah, so you're doing like when you're balancing, like checking for the balance, are you doing like 3 times 2
Oh
plus
yeah. Yeah. Hmm.
plus like, would this be like plus 2? Like 3 plus 2 plus 2 has to be equal to like 3 plus 3 plus times 2. So like, is that what you're doing?
So anytime you're balancing, you want the number of atoms to be the same on both sides.
Yeah.
This
Yeah.
also is going to be true for the number of electrons or charges on both sides.
Okay.
So yeah, so we should have 6 electrons that get transferred from the copper 2 plus to the uh aluminum solid.
Okay.
Yeah.
So you don't take into account like the solids. You're just looking at like the charged particles.
Oh, well, I'm taking into account the solids as well, but the thing that's different, well, the thing that's different is the charges, so that's what I need to balance.
Yes.
Hmm.
Um, okay, and let me just look at like what I'm trying to say, like if we go back to the answer choices,
Yep.
for D, then you would know like a shortcut that it's not balanced would be like if you multiply like 2 times the 2 plus on that copper and set it equal to like the 3 and the 3 plus, like you have an imbalance there. Would that be a shortcut?
Yeah, yeah. That was like when I wrote this. Um, yeah, when I wrote this, accidentally I wrote 2 plus, and then when I brought it down, it gave me like 4 electrons for the aluminum. So that's when I
Mhm.
realized that's a mistake. But yeah, for each of these choices, you can kind of think of it that way. So like think of like the electrons, or charges. So on the left for A, let's say like on the left we have the 6 positive, and on the right we actually also have 6 positive. For B, we have on the left, let me zoom in. So for B on the left, we have 9 positive. On the right, we have 4 positive. For C on the left, we have 6 positive, and on the right, 6 positive. For D on the left, we have 4 positive, and on the right, we have 9 positive. Like you're gonna have to like zoom in.
Yeah, I can see it.
Yep.
Yep.
So you want it to be balanced, right? So that means choice B is out, and that means choice D is out. So
Yeah.
A and C are balanced, but now we need to figure out, based on the reduction potentials, which is the thing that gets, you know,
Yeah.
reduced, which is the thing that gets oxidized.
Yeah. Which we already know is copper because
Yep.
it has a higher reduction potential.
Yep.
So it's good. This is good.
Mhm. So any other questions there?
Nope, this was
All right.
useful. I think I always struggle with like writing the
Yep.
reaction
Yeah. By the way,
reacts.
well, yeah, never mind. So okay, let's try this last one here.
A circuit similar to that in figure 2 is set up in which X equals lead, I think, and X and plus the cation of lead, Y equals copper, and the cation is copper 2 plus. Well, an oxidation reduction reaction occurs spontaneously. Okay. So we have, oh, is this they gave us they did. from the passage, they gave us the reduction potential for each one. And
So before you even look at that, what we
yeah,
can eliminate two choices.
if it's spontaneous, the E of the cell has to be positive, so I would eliminate A and C.
Wait, sorry, you said okay. And then so okay, why eliminate A?
Um,
Keep in
is
mind
the
that
E
there's
E of the
two
huh?
statements. Keep in mind that there are two statements here.
Oh, yeah, I was not seeing that.
Mhm.
Yeah, I was not seeing that. So, uh, spontaneous would mean yes, and it would mean negative. Uh, if
You mean
sorry, not
yes?
if it recurs, like I don't know, I'm getting confused. So if the E of the cell is negative, if is when it's spontaneous is negative. So if it occurs spontaneously, it's a question mark, would mean
Are you sure it would be negative? What's the
positive.
equation?
Positive. If it's
Okay,
spontaneous, it's positive.
all right.
It's late. My mind is
Yeah.
fried.
Yeah. It's okay.
Um,
But yeah, so you're right about eliminating C because if it's yes, meaning if it's spontaneous, your cell potential should be must be positive, right?
yes.
But if it's no, meaning it's not spontaneous, right? We would have to have a cell potential that would be negative, right?
Yes.
So what can we eliminate?
Um, B.
Yep. So a lot of times you can answer questions like this on like this in like the validity of the question that it's or the question stem or the choices that are being made, right? So yeah, like without even like what I mean is like you don't even need the question for this to be able to. I mean, maybe if you just ask like if it's spontaneous for the first part, but yeah, internally valid would mean this. So okay, B and C are out, and then what?
Um, then now we have to look at the numbers.
Uh-huh.
Um,
Oh yeah, I think I started writing out this calculation here. Um, yeah.
yeah, I remember we definitely did. We were reading
Yep.
through it.
So we're at these,
Yeah.
and they're both positive, so we should get a positive number that's larger than 33.339, right?
Yes. What, did I read the question right or no? Because I know it's did you already figure out which one? Oh, of course, because we know it has a lower, so you know that that what's gonna be reduced is copper and what's gonna be oxidized is lead. Okay, sounds good.
Mhm.
And so you just added and flip the sign, so added. We have to
Yeah,
add.
basically
Yeah.
all the way back here when we did this, I was writing this out uh for the cell potential here. But yeah. So yep, so that's how you do that one.
Yeah. So I guess one way that might be faster is to like add 340 plus 130 and then subtract 4 from it. And that should be the answer of, well, and the decimals, but yeah.
You said 330 times.
The 340 plus 130 and then subtract 4. Sense.
Oh yeah. Mm-hmm.
466. But it's not that. The
Yeah.
point.
Yeah.
Yep.
So, yep, that's correct.
Yep. Positive. Yep. So it's
Mhm.
D.
Yep. Good job.
Wow.
Yep.
Okay.
Mhm.
This was good. I feel like I learned a lot.
Yep. That's good.
Yeah. It's a
Yeah.
good passage to review.
Yep. Awesome. So, yeah, good job. And yeah, I think you understand everything here. So, but yeah, you can take your screenshot. I mean export.
Expert, yeah. Okay. Done.
Mhm. All right. So let's wrap up. So what are you going to do, like, I guess tomorrow?
I think I just want to continue doing my flashcards.
Uh-huh.
I'm just trying to get as many in before I do like an
The-
AAMC full length.
Mhm. Got it. So yeah, look through the PDFs folder. I'll scan the thing that I'm talking about. And also in the content consolidation folder, I have a spreadsheet that has a lot of stuff in it that includes a lot of oh yeah, includes a lot of terms and stuff.
Mhm. Yeah.
Here, I'm gonna just put it in the chat right there. Yeah, there's a lot of stuff that come up
Oh
here.
yes, I've seen this before. Yeah.
Yeah,
It's good.
yeah. So like all the way on the right, there's like development timelines and psych theories, behavioral sciences and stuff like that. So you can take a look at all that stuff. But yeah, so okay. And then tomorrow we'll meet to go over whatever you want to go over tomorrow. And
Yeah.
then we'll talk about like the specifics, but yeah, you'll take an AMC test. And um but I think I would want you to go through your psych soc tests that you've been doing, and then for every term that is new or that you don't know, just you know you know how to like add Anki cards, right?
Yeah.
So yeah, just add those Anki cards for the psych soc, because yeah, you don't want them to just throw some term at you that you don't know.
The other thing that I've been wanting to do is
Mhm.
like I feel like it would make me more calm. I've never like written
Oh,
down like
sorry, did you export it yet?
yes, I did.
Okay, yeah.
Uh,
Mhm.
I've never like written down formulas like in the like tutorial section, but I feel like for me it might be useful to write down the units, like the units and like the base SI units. If I can like come up with a quick way to write that on my like booklet, I think that would make me more comfortable for the
Yeah,
calculus
yeah,
section.
yeah. Whatever works, you know. Yeah. Uh, and I would also recommend the optics table.
Yeah, and that too. Yeah.
Yeah, yeah. So yeah, whatever works for you that you feel would be a good thing to reference, can definitely help out.
Do you
So
think that's, I mean, I guess I could go either way and it'd probably take similar amount of time to like formulas versus units approach on that.
uh sorry, again, you said take about same amount of time or whatever?
Like to write down actual formulas versus to write down just the units and like the uh SI base unit, like derivations.
Yeah, I mean, I think you know most of those already, but yeah, you can definitely do that in those, first 15 minutes or so. Um, but yeah, I also want you to write down, the different ways of expressing the density of water,
Yeah.
because what's easy to forget um is how like a cubic meter is 1,000 like liters. That might not be readily apparent.
Yeah.
So yeah, whatever you think, would help you write down at first, it could even
Yeah.
be like, some other things that I would think of, like for me would be like sarin versus threonine, like what are the difference in that, like what does that look like? So perhaps some molecules, like it's essentially going to be just things that the way that I view it is like I'm brain dumping the second I get to the test center, so I could put all that stuff on the paper or the whiteboard thing they have, uh just because I'm gonna be forgetting it like right away. So I'm just brain dumping that. So I would maybe draw like this is adenine, this is guanine, because sometimes I've seen them ask that. Also like biochem pathways. It seems like you haven't really had trouble with that stuff yet, but I would write maybe certain types of biochem like metabolic reactions or something like that. So
Yeah.
whatever you find works for you, yeah.
Yeah. I guess I just have to practice it and
Yep.
see what works best as well. Yeah.
Yep. Awesome. All right then.
Yeah.
So I will see you tomorrow, same time.
Yep.
All right, awesome. All right. Have a good one. Take care.
Bye.